In this video, I'm going to show you how to use the Hungarian algorithm to optimize the assignment of tasks to minimize something. The example we have today is of a construction company with 4 large cranes that they need to transport from 4 different depots to 4 different construction sites. As you can imagine, you want to minimize the distance that each one would have to travel because that would save time and money. The distances in kilometres between the cranes and the construction sites are given below. So you've got crane 1, 2, 3 and 4 and site A, B, C and D. And in there you've got the distance in kilometres. So for example, crane 1 is 90 kilometres away from site A and it's 75 kilometres from sites B and C. So you might think, well, that crane should probably be going to site B or C. However, it gets complicated when you've got lots of different items going in different places, and maybe that's not actually the best. Maybe it's better to send one of the others to B and a different one to C, and maybe D is the correct option here. Using the Hungarian algorithm, we're going to find it out. Now, it's a 5-step process. Step 1, well, we put it into a matrix. It was in a table before, which looks like a matrix anyway. Once we get that matrix, we need to subtract the smallest number in each row from each element in that row. So you can see in the first row 75 is the smallest number, in the second row 35 is the smallest number, and in the last 2 rows we've got 90 and 45 respectively. So taking them away from all of those elements, we get a new matrix that looks like this. Step 2, we do the same thing with the columns. We find the smallest number in each column and we subtract it from each element in that column. Now, I've already got some zeros here, so I've written in that the first 3 columns, the smallest number is all 0, so I'm taking 0 from each of those. You don't actually need to write that if you don't want to. I'm just demonstrating that that's the smallest number. In the 4th column, 5 is the smallest number, so I'm going to subtract that and I'll see what sort of matrix I get. So you can see now I've got a new matrix and I'm on to step 3. Step 3, I have to draw the minimum number of straight, horizontal and vertical lines that will cover all of the zeros in my matrix. So let's do that. I've drawn 3 lines here. There can be more than one way to do this, but you're looking always for the minimum number of lines. I've drawn 3. The second part of step 3 is to look at that and just consider, is that number of lines equal to the number of rows? If it is, I get to go to step 5. Otherwise, I have to go to step 4. And, well, it's only 3 lines. It's not as many as there are rows because there are 4 rows in this matrix. So I need to go to step 4. So step 4, I need to subtract the smallest uncovered number, that's in the whole matrix, from all of the uncovered numbers and add it to the numbers at the intersections of lines. So you can see my uncovered numbers are 50, 20, 25, 65, 50 and 65. The smallest one is 20. So I'm going to be subtracting 20 from the other numbers, except for I'm going to add it to 15 and 35 because they're at the intersections of the lines that I've drawn. This is what it looks like when I do that. I've taken 20 from all of those uncovered numbers and I've added it to the ones that were at the intersections. Now I'm going to repeat step 3. I'm going to draw the minimum number of horizontal and vertical lines that will cover up all of the zeros. Let's see what happens. 3 lines again. Sometimes you'll be lucky and you'll get 4 lines straight up. Sometimes you might need to do this process a couple of times. It's an iterative process, which means that you keep doing it until you get the right number of lines. So I'm going to have to go back to step 4 again. I need to look for the smallest uncovered number. It's 5. So I'm going to subtract 5 from all of the uncovered numbers and I'm going to add it to the numbers at the intersections. So you can see I've done that. I added 5 to 35 and I got 40, and I added 5 to the 0 that was under the intersection, and now I've got 5 there. So back to step 3, drawing the minimum number of lines that will cover all of the zeros. And I can do it like this. I can just draw 4 lines across like that, or I could do it the other way. Doesn't really matter, as long as I've got those 4 lines, and there's no way I can do it with fewer lines. I could not possibly cover all those zeros with 3 lines, so what I've done is correct. Now I get to go on to step 5. In step 5, I'm trying to find the number of zeros equal to the number of rows that have a column and a row all to themselves. I haven't worded that very well. Basically, I'm trying to cover up zeros here that such that each zero I do cover up is only in 1 row and 1 column, and I'll show you what that looks like. The first 3 red boxes there, each of those zeros has a row to itself. You can see that the 0 in the top row is not covering any others. The 0 in the second row, I'm not covering any others in that row, and the 0 in the third row, I'm not covering any others there. But you can see I've left a box out here because if I tried to cover up that 0 in the bottom left corner, you can see it would have to share a column with that other one I've covered up between the 60 and the 40. Can't do that. I have to arrange them in such a way that if I look at the columns and look at the rows, there's only 1 0 highlighted in each row and in each column. So it could look like this, where you can see now that each of those zeros is the only covered 0 in that row and the only covered 0 in that column. Usually there'll only be one way to do this, but sometimes you might find that there is actually more than one way to do it. So you can see I've just zipped it over there, but I could do it in a diagonal across there as well. So you might wonder, what's the point of finding all of these zeros that are by themselves and don't match up across rows or columns? Well, I'm going to get that pattern now, and I'm going to apply it to my original matrix. Let's see what happens. As they scoot across there, you can see that these values that I've highlighted are actually the optimal values for this situation. I've got 2 possibilities here, and I'll show you why they both work. If I add together the numbers at the top, I'm going to get 275 kilometers of distance for all of my things. If I add them up in the bottom, guess what I get? I also get 275 kilometers. So there are actually 2 optimal ways that we could go about this, and in that case we might think about other things that are important to us. I don't know, something. But anyway, most of the time, like I said, you'll just get one solution, but there is a possibility of more than one solutions if there's more than one way to arrange your the highlighting of your zeros at the end. So that's it. That is minimizing using the Hungarian algorithm. I hope that's made sense, and I hope I haven't made any mistakes.